Yes. So in the previous class, we were looking at the strain energy density function for a frame indifferent material. Okay. So now let us show the relation between the second Taylor stress and the strain energy density function, assuming that the material satisfies the axiom of material framing difference. So we have the following theorem now. So given elastic material whose stored energy function is frame indifferent. Given W tilde defined by W tilde of x comma c is equal to W hat of x comma under root of c for all c belonging to P sim. If we assume without loss of generality, now loss of generality, that del W by del C belongs to sim. Then S is equal to tilde of x comma c, which is S hat of x comma f is equal to S tilde of x comma c is 2 times del W tilde by del c. So it is twice the grade. Okay, so this is C is equal to F there belongs to P. Or equivalently, S hat of x comma e is equal to del W by del E of x e, where this function x comma e is equal to W tilde of x comma c, and e is equal to half of c minus I. So this is the theorem. And then conversely, so this is let's call this as 1. Conversely, if 1 holds, then the material is hyperelastic. With the hand of x comma f is equal to W tilde of x comma c. Okay, so let us try to prove this particular theorem now. So last time we have seen that, so we have seen that T hat, that is the first Euler-Markov stress, is the gradient of the strain energy density function with respect to F. So we should try and link the second Euler-Markov stress to this expression for the first Euler-Markov stress in terms of the strain energy density function. So let us write S hat of F is equal to F inverse times T hat of F. So this is just the relation between the second Euler-Markov stress and the first Euler-Markov stress, and so this is equal to F inverse times del W hat by del F of F. Right? And then now we try to write this in terms of the gradient with respect to C. So that is what we will try to do next. So so let us now find this directional derivative here. So del W by del F matrix inner product U is equal to D of F W hat of F in the direction of U. So this is nothing but the definition of the gradient in terms of the directional derivative. And now we will try to find this directional derivative in terms of the directional derivative with respect to C, which is F transpose F. So let us try to do that. So this is equal to dF of W tilde of F transpose F. So this is something we have proved, right? In the last class we showed that W hat of F is equal to W tilde of F transpose F. Right? So this is because of material framing difference. We use the polarity proposition and we were able to deduce this particular relation here. So I am using that relation here. So W hat of F is W tilde of F transpose F, and then we are using the chain rule here. So this is so first let us just write it in this way, and then now we can write this as dC of W tilde of F transpose F times D of F times F transpose F in the direction U. So this is just an application of the chain rule now, and so basically it is the directional derivative of W tilde with respect to C in the direction of the directional derivative of F transpose F, which is C itself, with respect to F. Right? So this directional derivative can be expressed in this particular way here. And then now you can simplify this particular expression here. So this subscript is just to show that the perturbation is on C in this particular case, and here the perturbation is on F. So this U is a perturbation on this F. So this directional derivative it is with respect to this F, whereas here it is with respect to C. So that just to clarify that, I am putting this subscript for the directional derivative here. So then this is W tilde of F transpose F times F transpose U plus U transpose F. And this we can write now in terms of the gradient. So this is del W tilde by del C evaluated at F transpose F matrix inner product of F transpose U plus U transpose F. And this can be written as, so we will use the properties of this tensor product. So that is A times B, C is equal to B transpose A, matrix inner product C, and so on. So those properties, you just go back to that. This is exactly of this particular kind here. So we'll use those properties here. So we'll get F times del W by del C evaluated at F transpose F plus del W tilde by del C evaluated at F transpose F. This the transpose of this matrix inner product. So now this del W by del C, we have said that without loss in generality it is symmetric. So that is actually fairly obvious, right? Because see, del W by del C ij is equal to del W by del C ji. Right? That is because C is symmetric. Okay, so that's where it is fairly obvious that this transpose, whatever you have written, is going to be the same as this particular object here, because it is a symmetric tensor, right? Because of this particular argument here. So that is why we said without loss in generality, so that we can always assume del W by del C to be symmetric. Okay, and then so we will get that. So let us now write this as so from this let us write S now. So S is equal to S hat of F, let us write that is equal to F inverse times del W hat by del F in the direction of F. So that is equal to this particular object here. So F inverse times this F will be just identity. So you will get that, so you will basically get this particular term. So you will get that this is del W tilde by del C evaluated at F transpose F plus del W tilde by del C evaluated at F transpose F transpose. And this is equal to 2 times del W tilde by del C. So that is evaluated at F transpose. And so that completes the proof that S hat of F is a function of C. So basically what we have shown is that the second pure of stress is actually dependent on C. So that we have already shown, but now we have also shown that it is the gradient of the strain energy density function with respect to C. So twice. Okay, and then now the second relation as a gradient with respect to E. So that also we can show using the chain rule. So let's do that also. So now del W tilde by del C matrix inverse of U is equal to dC of W tilde of C in the direction of U. So that is equal to D of E W tilde or let me call it W check. Okay, so this is a new function that I am denoting here. So this is E. So again, it's very similar to the previous proof. So this is D of C of E in the direction U. So again, I'm just simply using the chain rule, just exactly like I did it in the previous case. Now again, I'm applying the chain rule in this particular case here. So this is equal to dE of this W check of E that times U by 2. So this relation comes because E is equal to half of C minus I. Okay, so when you perturb the C with U, you get half of U. So that is the reason that you get this U by 2 here. And this is equal to, now it's linear in the direction. So the half can come out. So that is half of dE times W of E times U. And this is equal to half of del W by del E matrix inner product of U. And then from this, now you can see that, so this implies that S of E is equal to del W by del E. So it's the gradient of the strain energy density function with respect to E. Okay, so that shows that the second of stress can be directly obtained as a gradient of the strain energy density function with respect to E itself. Okay, now we have not yet made any assumption about isotropy. Right? So now let us look at isotropic hyperelastic functions. So yes. So let us look at that now. theorem. Okay, just one thing is actually the converse I forgot to prove in the previous theorem, but that is fairly straightforward. So just reverse these steps and then you will get the converse. So that basically if you are given that S hat is equal to del W by del E, then the material is hyperelastic. That is because again just if you reverse the steps, then you will get that S hat of F is equal to F inverse times del W hat by del F. Okay, so that's just a reversal of the steps and you will get that the material is hyperelastic. So I think that part is fairly trivial, so I'm not proving that converse. So that's why we are just going to the next theorem now. So the stored energy function now, the stored isotropic. X, if I believe, now W hat of X comma F, so this should be W hat, right? W hat of X comma F is equal to W hat of X comma F cubed. So let us try to prove this. So recall that in when we are talking about material frame difference, so at that time we had W hat of XF is equal to W hat of X comma Q times F. So it was the F was pre-multiplied by Q. Now when we are talking of isotropy, it gets post-multiplied by Q. Okay, so that is the difference between the two cases here. Fine. So proof. So W hat is isotropic, if and only if T hat of F times Q is equal to T hat of F. Sorry, that is T hat of F cube. So this is the condition for isotropy. I mean, again, this condition is derived from the relation for isotropy for the Cauchy stress. Okay, so from that you will get this particular relation for the relation between the for an isotropic material for the first pure of stress here. And now if you express this in terms of the so let me just rewrite it. So this implies that T hat of F is equal to T hat of F times Q transpose. Okay, so now in terms of the gradient with respect to the strain energy density function, we will get del W by del F evaluated at F is equal to del W hat by del F cube times Q transpose. Okay, and then the proof is very similar to the case of the proof where we showed that W hat of XF is equal to W hat of X comma Q of F. So in the case of material frame difference, so the proof is going to be very similar to that. So we will define this function now W of Q, and then the steps are very similar to that earlier proof. So let me just go over that proof very quickly. So let W hat of QF is equal to W hat of F cube. So we are dropping the dependence on this X just for notational convenience here. Okay, so now let us find the gradient of this of this particular function here. So you will get that analogous to the previous proof, right? Previous proof using MFI, right? Using material frame indifference. Now, in this particular case, you will get that del WQ of F by del F is equal to del W hat of del F evaluated at F times Q transpose. Okay, so very, very similar to the proof which we have already used when proving MFI. So at that time we get this one. Now let us call this as 1 and let us call this as 2. So from 1 and 2 you can see that the right hand sides are the same, correct? And so hence the left hand sides are also the same. So let us show that. So from 1 and 2, so from 1 and 2 we will get that del W hat Q F evaluated at F minus del W hat by del F evaluated at F is equal to 0. And then now you can write this as del by del F of WQ of F minus W hat of F is equal to 0. And then just like in the previous one, so suppose now if you have WQ of F is equal to W hat of F, then this is trivially satisfied. Conversely, if suppose this relation is equal to 0, then this implies now that W hat of Q of F is equal to W hat of F plus C of Q. Right? So this is exactly as we did it in the last class. And then we had shown there that this C of Q goes to 0, correct? So that is again you have to choose F is equal to identity, then you have to choose F equal to Q, then you choose it to be Q square and so on. So the same procedure whatever we followed in the last class when we were doing the proof for the MFI case. So same kind of thing you now carry it out in this case also, and then what you will get is that you will get C of Q is equal to 0 in this particular case. So so similar to the previous proof again. So similar to the previous proof. Proof, you will get that C of Q is equal to 0. And then that is why you will get that W hat of Q of F is equal to W hat of F. So basically now what you have got is W hat of FQ is equal to W hat of F. Okay, so in MFI we had W hat of QF is equal to W hat of F, and now for isotropy you have W hat of FQ is equal to W hat of F. Okay, so now we are going to combine these two notions of isotropy and frame indifference. See, in this particular proof I have not made any use of material frame indifference, right? But material frame indifference is an axiom that we can always appeal to, correct? Because it's an axiom, and so we can always use material frame indifference, and so that is what we are going to do next. So that means, but remember that isotropy is an assumption. Okay, isotropy, I mean, a material may be isotropic or it may not be isotropic, but MFI is always there, right? Because that always works. So that is, so now as I said, we will combine these two notions of isotropy and material frame indifference to get a reduced form for the strain energy density function. So what we are going to see is that basically the strain energy density function depends on the invariants of C, which are the same as the principal invariants of B also. So C and B being the right and the left, right and the left Cauchy-Green strain tensors. So let us see that now. So theorem again, stored energy density function. The stored energy W hat from V0 to lim class to R is hyperelastic material. Is frame indifferent. Is anisotropic. If and only if there exists a function W from invariance of P sim to R such that W hat of x comma f is equal to W hat W of x comma invariance of f transpose f, which is also equal to the invariance of f transpose. So that is the theorem. So for all f belonging to lim plus. So let's try to show this result now. So as I said, we just need to combine the two options or two notions of isotropy and frame indifference here. Fine. So let us prove this. So first thing, proof is that the invariance of C is equal to F transpose F and B is equal to F transpose are the same, are the same, because we have seen that they are orthogonally equivalent, correct? So they are linked to each other through R and R transpose. So that we have already seen that, and so the principal invariants are the same. So this part is trivial because the principal invariants are the same. So we just need to show the first relation in order to do this here. Fine. So then we have now that W tilde of F transpose F is equal to W hat of F. Right? So this is MFI. Right? We have already shown that the dependence on F goes to a dependence on C. Correct? So that is just MFI. And this here is equal to W hat of F times Q. So this is now isotropy. And now again use this. So this is again MFI. So W tilde. So this is again MFI. W tilde of Q transpose F transpose F times Q. And so what we have shown, so this F transpose F is the same as this object here. And so what we have shown is that this W tilde is an isotropic scalar value function of C. Correct? So that is what we have shown here. And because of that, so W tilde is a scalar valued isotropic function of C. So tropic function of C. And so you will get that W hat of x comma f is equal to, by the characterization of a scalar valued isotropic function, it has to be a function of the invariant, right, of C. So that is F transpose F. So that shows this particular thing here. And it's an if and only if. So we also need to show the converse of this one here. So conversely, so converse is actually easy because the moment you say that you have such a function, then it is very easy to show that MFI and isotropy are satisfied in this case. So let us just show that converse also. So conversely now, if W hat of F is equal to W of invariance of F transpose F, then W hat of F is equal to W tilde of Q of F is equal to W tilde of F. W tilde of FQ. That is because since the principal invariance of Q F transpose times Q F, which is equal to F transpose F, and FQ transpose times FQ, which is equal to Q transpose F transpose F times Q, are the same as those of F transpose. So in this case, you just get back F transpose F, and in this case, this is orthogonally equivalent. So the eigenvalues, principal invariance, and everything will be the same as F transpose F. And so basically, so because that function exists, right? So we just need to show that. So suppose if you replace this by FQ, right? Then we need to show that. So here also you need to replace it by FQ. And so what we have shown is that the principal invariance of this FQ transpose. So in place of this F, now you are putting FQ. So FQ transpose times FQ. So that is Q transpose. And then similarly for this other case also. And so that is how we will get that if you have the existence of a function that is a function only of the principal invariance of C and B, then the material is automatically isotropic and it satisfies material frame indifference. Okay, so now the next step is now to relate the second theorem of Gauss stress to this particular function here, which is now so what we have shown is now that this function for an isotropic material, it's a function only of the principal invariance of C. So let us now try to find the expression for the second theorem of Gauss stress as a gradient of this particular function here. So let us do that. So that is the next theorem now. So theorem. So let W hat be of the form W hat of x comma f is equal to this W of x comma invariance of f transpose f, right? For all f belonging to lim plus, for all f belonging to lim plus. And then after this we get that p hat by 2 of x comma f is equal to del w by del I1 times f plus del w by del 2 of I1 I minus ff transpose times f plus del w by del I3 times I3 times f inverse transpose. And this is the expression for the first theorem of stress. And then similarly the expression for the second theorem of stress is S tilde of x comma c is equal to del w by del I1 times I plus del W by del I2 of I1I minus C plus del W by del I3 times I3 times C inverse. And this can also be written in another form, so that is equal to del W by del I1 plus del W by del I2 times I1 plus del W by del I3 times I2 times I minus del W by del I2 plus del W by del I3 times I1 times C plus del W by del I3 times C squared. Okay, so these are just alternate forms that are obtained by using the Cayley-Hamilton theorem. So actually once you get this particular form, just substitute C inverse in terms of C square using the Cayley-Hamilton theorem, and then you will get this particular form. So, so this is just a trivial step from this particular step. So we need to show basically this step and then this particular step. That's all that we need to show. But one more thing before that, we also will give the expression for the Cauchy stress also in terms of these gradients here. So the Cauchy stress is J by 2 times tau hat of x comma b is equal to del W by del I1 times b plus del W by del I2 times I1 of b plus minus b squared times plus del W by del I3 times I3 times identity. And again, using the Cayley-Hamilton theorem, you can replace b squared in terms of b inverse. So we can also write this as del W by del I2 times I plus del W by del I3 times I3 times I plus del W by del I1 times B minus del W by del I2 times I3 times B inverse. So you can also write it in this particular way here. Okay, so now as I said, there only that one statement needs to be proved. After that, we will get all the remaining relations here using the relation between the first pure effect of stress and the Cauchy stress here. So let us show, so what we will do is, we will first show this particular relation, then this relation will just follow because T is equal to F times S. So just, you can see that if you just multiply this particular relation by F, you will get this particular relation. And then similarly, you will use that tau is equal to F transpose divided by J. Right? So this relation if you use, then from this relation, you will also get this particular relation. Okay, so these relations will be, so if once I prove this particular relation, then the relation for the first pure effect stress and the Cauchy stress, they will just follow from the relations between the three types of stresses. Okay, so further, so all that we need to do is just simply prove this. And I already mentioned that this is just obtained using the Cayley-Hamilton theorem, and then similarly, this is also obtained from this using the Cayley-Hamilton theorem. So that will show all the results here. Fine. So as I said, this is the only statement that I need to prove. So it's just a matter of taking the gradient, right, with respect to the this one. And so what we will get is that, so we have seen that S is 2 times del W by del C. Right? So we are just going to use this particular relation here. So I can write S tilde by 2 is equal to del W by del I1 times del I1 by del C. So this is nothing but the chain rule again. So del W by del I2 times del I2 by del C plus del W by del I3 times del I3 by del C. Right? And then from this you will just get that this is equal to del W by del I1 times identity. So del I1 by del C is just the identity tensor plus del W by del I2. So this is nothing but the this is trace of cofactor of C. So that gradient we have already seen in the tensor part. So this is trace of C times identity plus minus C plus del W by del I3 times cofactor of C. And then as I said that use Cayley, use Cayley Hamilton, and the relations D is equal to F times S and tau is equal to Fs F transpose by J to get the remaining relations here, to get the other relations. So, okay, so that completes this particular proof. But now, so this is an extremely important result. Okay, so let us just analyze this particular result here. Okay, so if you look at this particular expression now, okay, so this is S by 2 is this particular expression. So let us just go back to the result when we had not assumed the hyperelasticity, right? So let us look at that now. Yeah, so if you recall, we had shown that S is equal to gamma naught of the function of the invariance of C plus gamma 1 of the function of the invariance of C times C plus gamma 2 principal function of the principal invariance times C squared. So this is what we had shown, correct? And then, okay, so this, as I said, that this is just C inverse, so that you can replace with C squared. So some other function here. So now what is the change that has happened by assuming hyperelasticity? So that is very important here. So you see that when we derived this particular formula, we had not assumed isotropy, and so you can see that there are 3 functions that need to be determined, right? These are 3 different functions that need to be determined. So obviously that is a much more difficult task than now. Here if you assume hyperelasticity, then only one function now needs to be determined, right? And so that is this function. Just I need to determine this particular function here, right? So if I can determine the strain energy density function in terms of the principal invariance of C, then all these other coefficients, right, they automatically are now just gradients of the just the derivatives of the strain energy density function with respect to I1, I2 and I3 and some combination of those things. So that is what you can see. So so to summarize now, if we assume hyperelasticity, then the task of finding the constitutive relation for an isotropic frame indifferent material reduces to only finding the strain energy density function as a function of the principal invariance of C. That's it. So only one function you need to find. You don't need to determine these 3 functions. When we had not assumed hyperelasticity, we had to determine 3 functions. Now we have to determine only one function, and so the coefficients will then automatically get fixed as derivatives of the strain energy density function with respect to the principal invariance. So that is the big advantage of assuming hyperelasticity. So as I said, that actually the hyperelastic material, so strictly speaking, actually hyperelasticity is a subset of elastic materials, but if you see the literature, the moment they assume elastic material, they will also assume hyperelastic. So at least I have not seen that any material model where it is elastic, non-linear elastic, but not hyperelastic. I have at least not seen any such model in the literature. So typically you will assume that there is nothing here. Basically there is no material model here. So this hyperelastic and elastic are sort of used synonymously, so to speak. Okay, fine. Then fine. Then so what about the Saarinatic of material, right? So let us look at the strain energy density function for a Saarinatic of material. So theorem. So a Saarinatic of material. Material. So that is S is equal to lambda trace of E times identity plus 2 mu E. So this we have seen in the previous class. We analyzed this Saarinatic of material in very great detail. So this is hyperelastic. Is hyperelastic with W of E is equal to lambda by 2 of trace of E square plus mu times trace of E square. So this actually one can show this very easily, and you can also express this in another form. So this is also equal to mu times I1 minus 3 plus lambda plus 2 mu divided by 8 times I1 minus 3 square plus minus mu divided by 3 of I2 minus 3. So okay, so yes, so you can see here. So okay, we will show this, but before that, you can see that it is a function of the principal invariance of E itself, and so because it is of C, which is the right quotient strain tensor. So you can see from this that because it's a function of the principal invariance of C, it is automatically hyperelastic and isotropic, and it also satisfies material framing difference. So that is because the theorem was an if-and-only statement, that if the strain energy density function is a function of the principal invariance of C, then the material is isotropic and it also satisfies material framing difference. Right? So here we are just simply showing that it is indeed a function of the principal invariance of C, and hence it is it satisfies MFI and it is an isotropic material here. So all we need to show is this particular thing. So that actually is fairly trivial in the sense that we just find the gradient of this strain energy density function with respect to E and show that that is equal to this expression here, that is S is equal to lambda times trace of E times identity plus 2 mu times E. So let us show that. So that is just as usual, we just find the directional derivative here. So W of E plus U is equal to W of E plus lambda trace of E times trace of U plus 2 mu times trace of E U plus order of U. So just put E plus U and then the usual stuff about expanding it out and so on, and so this is what you will get here. And then this is equal to W of E plus lambda trace of E times identity plus 2 mu times E matrix inner product of U. And so this is the gradient. So this is W by del E, because that is the definition of the gradient of a function with respect to the Green-Lagrange strain tensor. And so that shows that your second kilohertz of stress is a derivative of the strain energy density function with respect to E. And so that is what we have now shown here. Fine. So, so now let us look at this a little bit more closely. So as I already mentioned that because the strain energy density function is a function of the principal invariance of C, it is automatically isotropic and frame indifference. Okay, so but see, so this is a very, very important point that I am now going to mention, that simply because a material model satisfies material frame indifference, it does not become a good constitutive relation. And so the Saarinen-Kirchhoff material is a very good example of that. So you will see that actually the principal invariant I3 is missing from this one here, right? So there is no dependence here. So note that there is no dependence on I3. Note that no dependence on I3, right? And that is actually a very major shortcoming of this particular model here, because if you see dV, right, is equal to J times dV naught, right, and so that is equal to under root of I3 times dV naught, right, so where I3 is the determinant of C. And so you know, so if you try to squeeze a material, right, and try to reduce its volume to 0, correct, you would expect that the strain energy density function should blow up, correct, so that to prevent dV from going to 0. So there should be some penalty in the strain energy density function, that as your J tends to 0 or I3 tends to 0, your strain energy density function should blow up. But here you can see that there is no such penalty, correct, and so that is also a very severe shortcoming of the Saarinen-Kirchhoff material. So, so as I said, this is an extremely important point. So many times you will see papers, they just say, oh, it satisfies frame indifference, but that doesn't mean anything. But just so let me put it like that. That basically material frame indifference, satisfying material frame indifference is a necessary condition for a good constitutive relation, but it is not sufficient to ensure that the constitutive relation is appropriate for whatever material that it is that you are trying to model. So that, as I said, that is an extremely important point here, and that is very well illustrated by this Saarinen-Kirchhoff material. So it satisfies the necessary condition. So by necessary condition we mean that this MFI condition should not get violated. That's what we mean. So suppose if there is a material model that violates material frame indifference, then we can reject that material model straight away, okay, because it doesn't satisfy material frame indifference, unless of course you are looking at some approximation, but then maybe you can tolerate a violation of material frame indifference, and in fact that is what happens in the case of linear elasticity, as we will show. But okay, but strictly speaking, suppose you want constitutive relations to satisfy all your axioms of continuum mechanics, then if a constitutive relation violates material frame indifference, then it is not an admissible constitutive relation. But now take the case where it satisfies material frame indifference. Okay, so it has satisfied the necessary condition, but that alone is not sufficient to ensure that that constitutive relation is a good constitutive relation for that particular material. Okay, so just to give a very extreme example, if I use the constitutive relation for a fluid for modeling steel, let us say, so that satisfies material frame indifference. So if I take a Newtonian constitutive relation for a Newtonian fluid, then it satisfies material frame indifference. But that constitutive relation is in no way appropriate for modeling steel, right? So in the same way, so in the same way that just if a material, if a constitutive relation satisfies material frame indifference, then we still have to carry out experiments to verify whether that particular constitutive relation is appropriate for that particular material. So there is no escape from actually conducting experiments and testing whether that particular model fits the experimental data. Okay, so there is no escape from that. Basically, so that is what you have to bear in mind. And this is applicable for all types of materials that we are going to consider. So that means whether you are considering elasticity, plasticity, fluid mechanics, whatever, any kind of material. If you are talking of constitutive relations, there is no escape from experiments. Okay, so you have to have a model that fits experimental data for different kinds of experiments, right? I mean, so you can use maybe one set of data or a few sets of data to fit the constants in your material model, but once this fitting is done, then now your constitutive relation should be able to predict the response in a new situation where where that experimental data has not been used to find your material constant. And so only when it fits that kind of experimental data, then you can say, okay, now this constitutive relation is appropriate. So suppose if you find that it is not appropriate, then you change the form of that constitutive relation and then again try to fit the experimental data and so on. So it's an iterative process. And so that is what happens. So let us take the example of rubber type materials here. So you'll see that in so Treloar had generated a lot of experimental data for rubber. Okay, I mean way back maybe 1950s or something of that order. And then we had lots and lots of models that were trying to fit this particular data. So you have Muni-Rivlin and Ogden material and Aruda Boys and Yao and Gent model and so on and so forth. So all these models, see basically because you cannot get that correct form of the constitutive relation, right? It is a bit of guesswork that is required. So you have to guess that strain energy density function, the form of the strain energy density function, and then try to get the constants by fitting it against the experimental data. And as I said, that once this fitting is done, then it should be able to predict the response in the case where where it's new data. That means a new piece of data it should be able to fit. So as you can see that constitutive relation is a very complicated business. Okay, and it grows more and more complicated when you are looking at let's say plasticity and viscoelasticity and all that kind of stuff. So it gets even more complicated. So here actually in the case of nonlinear elasticity, at least we know that it is a function of the principal invariance of C or B. But in the case of plasticity, we do not even know on what kinematic variables it should depend. And so there are so many different types of models when you come to modeling plasticity and viscoelasticity and so on. Okay, so people will use all kinds of internal variables, or they will use decompositions like FEFP, and then they will have an evolution equation for FP, and so on and so forth. So the story gets more and more complicated as you try to model, as you go outside the regime of nonlinear elasticity, the story gets more and more complicated. But unfortunately, that is the reality. And so what I would say is that basically constitutive modeling is the weakest link in continuum mechanics. Okay, in the sense that see all the other places, like if you take all the balance laws, like balance of linear momentum, angular momentum, etc., there is no ambiguity in the laws, right? But once it comes to the constitutive relation, then there is ambiguity, that we do not know what constitutive relation to adopt for some complicated material behavior. And so I would say that that is the weakest link in continuum mechanics. And as you know, a chain is as strong as the weakest link. That is a saying, right? So if you have a chain, right, made of links, and suppose if one of the links is very weak, then the chain will break, even if the other links are very strong. And that is precisely the situation in continuum mechanics, that the constitutive relation part is so problematic that the predictive capability that we have for as I said, complicated material behavior. I mean, if you take things like sand and all, even it gets even more complicated and so on. So, or porous materials, or non-Newtonian fluids and things like that. So, so the predictive capability becomes very, very weak in continuum mechanics, because we do not know what the constitutive relation is for these complicated types of material behavior. So this is so basically this is just the beginning of this topic of constitutive modeling, and what I would say is that constitutive modeling remains one of the most challenging unresolved problems in continuum mechanics. That is what I would summarize from this entire situation. But because the situation is a little bit nice in the case of nonlinear elasticity, we are able to at least give these results, whatever we have given so far. But the moment you step outside the elasticity regime, things become very problematic. Okay, so this is what we have to gather from this whole discussion on constitutive relations here. Okay, so I think we'll move on now to the next topic here. So we are going to talk about now the elasticity tensor. Okay, so yeah, so elasticity tensor. So basically, the elasticity tensor that we are going to consider is actually going to be useful in the linearization of the equations to derive the equations of linearized elasticity. Okay, so we are going to consider only the derivative of the first Euler Kirchhoff stress near to the reference configuration, that is f equal to identity. Okay, so that's the specific context that we are going to look at. In general, this derivative need not be evaluated at the reference configuration. Then that would become a general fourth order tensor and so on, which would be useful in finite element implementations of the total Lagrangian method and so on and so forth. But here our interest is a very narrow one, in the sense that we just want to linearize the nonlinear equations to get the equations of linearized elasticity. And so this particular elasticity tensor that I am going to talk about is actually going to be evaluated at the reference configuration, where f is equal to identity. Yeah, so this so the behavior of the constitutive relation, relation T is equal to T hat of f near f equal to I, is governed by the linear transformation C min to min defined by C x is equal to d of d hat of x evaluated at I. So I will first, just a matter of notation, I will put this slash in this C, because so as to not confuse it with the right Cauchy-Green strain tensor. So this C is actually the Gattau derivative of the it is the Fresher derivative. I'm sorry, not the Gattau derivative. It is the Fresher derivative of the first pure order stress, and so it's a fourth order tensor that basically it is a constitutive tensor thatCijkl that appears in linear elasticity. So this is the same object here. So it's defined as the Fresher derivative of the first pure Markov stress evaluated at f equal to identity. So as I said that actually you can evaluate it at any arbitrary f, and as I said that would be useful in the finite element implementations when you are trying to find a tangent stiffness matrix in a nonlinear implementation. That is what would appear there. But here, as I said, that our interest is a narrow one, and we are just interested in finding the linearized equations of linearized elasticity, and so there we are concerned only with small perturbations of the reference configuration, right? That is the whole idea behind linearized elasticity, that the u, the displacement vector u, is small in some norm sense, right? And so, so this is exactly the object that we are going to need when we carry out that linearization here. So as I said that let me just give you the initial notation form of this one here. So this is aCijkl and x comma f is equal to del Tij by del f kl. Okay, so this is evaluated at x comma f. And so as I said that you know, basically plays a key role in linearized elasticity. Linearized elasticity. As I said, it's going to be the same thing. You know, that this is what appears in your generalized Hooke's law,Cijkl. So this is exactly the same object as what appears there. While carrying out now the derivation, so we'll find various properties of this constitutive tensor C, but in finding these properties, we'll assume that the residual stress vanishes. Okay, so assume that the residual stress vanishes. Stress vanishes. So that means tau hat of I is equal to t hat of I is equal to s hat of I is equal to 0. So then the reference configuration, basically before the application of all the loads, there is no residual stress in that. So this is something that we will assume in carrying out the various derivations here. Okay, so the first result that we will show is that it is also the derivative of the second pure Markov stress, and it's also the derivative of the Cauchy stress evaluated at I. Okay, so let us look at that first. Okay, so C is equal to D of tau hat of I is also equal to D of T hat of I is equal to D of S hat of I. Okay, so we'll write now. So let us prove this. So basically, by definition, this is true, but we also now show that it is the pressure derivative of the Cauchy stress also, and it's the pressure derivative of the second stress also evaluated at f is equal to identity here. So let us use the relation that tau hat is equal to t hat times f transpose divided by determinant of f. Right? And so we will use this relation to find d of t hat of f in the direction u, that is equal to minus 1 by det f square times d of determinant of f times in the direction u times t hat of f times f transpose plus 1 by determinant of f times t hat of f times d of f transpose in the direction of u plus 1 by determinant of f times d of t hat of f in the direction u times f transpose. Okay, so and we have to evaluate all of this at f equal to identity. So you will see that when you evaluate, so this t hat of f when you evaluate at identity is 0, because we have assumed that the residual stress is 0. Correct? So this is so t hat at f evaluated at f is equal to identity is equal to 0. So this term will go away. Similarly, this term will also go away. Right? And so what you will get is that so evaluating at f is equal to identity and using t hat of identity equal to 0, we will get the first relation. So basically, you can see from that let's see this one here. So just substitute f equal to identity, then determinant of f is determinant of identity, which is 1, and then this is identity transpose, so that is also identity. So you will get that d of tau hat of f in the direction u is equal to d of t hat of f in the direction u, and so hence you will get that c is also equal to d of tau hat evaluated at the identity tensor here. And then similarly, you can use the relation between the first Taylor Kirchhoff stress and the second Taylor Kirchhoff stress also. So similarly using t hat of f is equal to, so t hat of f is equal to f times s hat, and so you will get d of t hat of f evaluated in the direction u is equal to d of f in the direction u into s hat of f plus f times d of s hat evaluated at f in the direction u. And then again your s hat evaluated at identity is 0. So s hat at identity is equal to 0, and then again you will get back the same result, because again you will substitute f equal to identity. So you will again get back that c is equal to d of s hat evaluated at I. Okay, so this relation also you will get. Okay, so we will prove some properties of thisCijkl in the next class. So basically, what we call as minor symmetries, we will show the next time. So that isCijkl is Cijkl is equal toCijlk. So these are what are known as minor symmetries. So that means it's symmetric in the first two indices, and it's also symmetric in the next two indices. So those are some properties that we will show in the following class.